Yeah.
It'll just be something
If there's
quick.
something
I
that really
take a
is
look
not
at it.
gonna work,
Okay, so let's go back over this again. The rate at which people are getting head injuries overall is 15%. So the people that have no helmet on, we'd expect 15 out of those 100 people to get a head injury. Similarly, if they have no helmet on, we'd expect the same number of people, the same rate for those two groups. This is our expected number of head injuries. That if there's no difference between, if there's no hypothesis that there's no difference between the risk of getting head injury if you wear a helmet versus if you don't wear a helmet, that's our null hypothesis. Let's say that what we see, in fact, echoes this, that's really what we see when we look at the 200 people, right? And we say to ourselves, oh, okay, that's great. That means that the expected values are 1585, 1585, and my observed values, the ones I actually observed, were 1585, 15, and 85. And if I look at each one of these cells, there's no difference between this cell, no helmet with a head injury, no helmet and head injury, or a helmet and head injury and helmet and head injury. The differences between all those cells are zero. So if I added up all the differences, all of the differences between those cells would be zero as well. Well, let's say that this is not true, or let's say not even that it's not true, but a certain amount of this can be ascribed to chance. We wouldn't expect to get exactly 15 people, even if it were true that there's no difference. We wouldn't expect that if we randomly sampled 100 people injured in a bicycle accident in an emergency room that were not wearing a helmet, that we'd get exactly 15 out of 100, even if the rate for that population was 15. Maybe we happen to get 30. And maybe when we looked at, or maybe we happen to get, say, 20. And maybe with no helmet, we happen to get 10. I'm just doing that so like the numbers stay the same. So we'd have 80 people that didn't have a head injury. We have 90 that didn't have a head injury wearing a helmet. Now there's a difference. Now the question becomes, is that difference between what we expected, which is basically the same rate for helmet and no helmet, versus what we observed, is that due to chance, or is that due to the fact that wearing a helmet is protective, or not wearing a helmet increases your risk of having a head injury? While we're looking at this, I'm going to just take my observed values, because really when you're collecting data, the first thing you see are your observed values, aren't they? Right? I'm going to take my observed values and I'm going to calculate something called risk. You talked about risk and you talked about odds upstairs. Okay? Whoops. Okay? Risk is the probability of having a bad outcome, right? This head injury, if you have either an exposure or no exposure. So if you have an exposure, which in this case you're not wearing a helmet, right? You have the exposure, your risk of having a head injury is going to be equal to 20 over 100. 100 people wearing a helmet, not wearing a helmet, 20 of them have head injury, the risk is 20%, 0.20. Okay, the risk if you're wearing a helmet is 10 out of 100. Whoops. Okay, now what can we see here? We can see that the risk without a helmet is 20%. The risk with a helmet, based on these observed values, is 10%. Let's turn this into something that maybe is pretty descriptive of what the increase in risk is. And let's call that the risk ratio. Okay, anytime we talk about a ratio, we're talking about a fraction. So we're going to say the risk is 20% if you don't wear a helmet, divided by 10% if you do wear a helmet. Your risk of being injured if you don't wear a helmet is twice as great as it is if you do wear a helmet. That's our risk ratio. Pretty simple, right? Complicated? No. Okay, now let's look at odds. Odds gets a little bit more confusing because as Levi mentioned in the lecture, it's not really that intuitive. Anybody here play the ponies or go down to Florida and play the greyhounds or anything like that? You know when they put up on the tote board, they put the odds up? Those are not risks. Those are really odds. For instance, if they say a horse is 3 to 1, What they're saying is that the horse ran if the horse ran 4 times, he would lose 3 times and win once. So you win 3 times your money, your $2 bet. Pays $6 for a $2 bet. If the odds are 3-2, that's basically saying if the horse ran 5 times, he'd win 3 and lose 2. Excuse me, lose 3 and win 2. Right? Get it? Okay, so odds are different. When we look at odds here for our observed values, I'm going to repeat this now for odds. When I look at the odds here, instead of saying 20 over 100, what do you think I'm going to say? 20 over 80. There you go. Right? So the odds are 0.25. In other words, for every 5 people that come into the emergency room with no helmet, 1 of them would have an injury, 4 of them wouldn't have an injury. That's the difference between odds and risk. I'm going to do the same thing with a helmet. Okay, it's equal. The odds are 10 over 90. Okay, which is a little bit more than 10%. Okay, so what's our odds ratio? Our odds ratio, again, is going to be a fraction. It's going to be equal to the odds if you're not wearing a helmet divided by the odds if you are wearing a helmet, and it comes out to 2.25. Now, your odds are 2.25 times greater. Your risk is 2 times greater. Okay. Now, you can use these kind of interchangeably when you want to describe or analyze these kinds of events. Now, if there's no difference between wearing a helmet, if our null hypothesis is true, we're back up at the top there. What do you think the risk ratio would be and the odds ratio would be equal to? 1. Exactly right. It would be 1 because it would be 15 over 100 divided by 15 over 100. And the odds would be 15 over 85 divided by 15 over 85. So what we need to now have is a function that'll let us be able to tell whether the difference between our observed values and our expected values are due to chance or really due to difference in the risk of having an injury due to an exposure, having an illness or an injury due to an exposure. And there's 2 ways that we can do this. One way is to look at the differences between these 4 cells. How different are these numbers, 15, 15 from 20 and 10 from the 15, 15 that we would have expected. And the other way is to examine our odds ratio and our risk ratio to determine whether or not they'll give us a hint as to how likely it is that the differences are due to chance or not. Okay, so now let's take an example. Okay, now this example is on Blackboard. You can open it up if you want to. And basically what I've outlined here is a study where we followed, over the flu season, we followed 98 people, and 46 of those people used paper in washing up and cleaning up, and 52 of those people were told to always use the hot air device to see if there was a difference in how likely it would be that they got the flu during the course of a season using paper or using hot air in a washroom. Okay, so this is a fake study, obviously. These are not real numbers. But what we would wind up with is kind of what you might wind up if you did your own study or if you're working with data that's in one of the various databases that we've provided. I just want to see the comments here to make sure the people at home are not having an issue. Okay, no problem. Okay. I'm sorry, say again. It's under Blackboard. It's on the lab session, and it's called Paper Air Excel, I believe. If it isn't there, let me know and I'll make sure it's not there. Okay, I'll put it up there right now. I'll make sure it's there right now. I thought I had it there. Maybe I don't have this version there, which would explain why it's a different name. Okay, yeah. That's going to wind up being a simple homework problem for you guys. But nothing, when you're in a hurry, nothing works well. You know, this little worm chasing itself up there in the corner. Okay. And let me go into lab. I'm going to put 2 files there, as a matter of fact, because As soon as we get done with this, we're going to run over to Excel and we're going to repeat this analysis. Lab session. Okay, data files. And I'm going to add to the data files. Okay. And in just a moment, they should be accessible to you. There you go. You should be able to get to them now. Paper versus air, Excel is the document I'm working with right now. I'll just minimize that in case I have to go back. Okay, so now if you look behind me, you can see, I hope, right? Yes? Okay, I'm going to get this out of the way. If you look behind me, you can see that out of 46 people that used paper all the time, 19 of them became ill. Out of 52 people that used hot air all the time, 10 of them became ill during the course of the flu season. So let's see what the risk would be of using paper versus hot air. So what would the risk for using paper be of getting sick? Volunteers? Right? 19 out of 46, right? Okay. Okay, and what would be the risk for using hot air? It's going to be 10 divided by 52. Okay, and the risk ratio is going to be equal to 0.41 divided by 0.19, okay, or 2.15. What about odds? The odds are going to be 19, oh, exactly, great, you're getting the idea, over 27. And for paper, it's going to be equal to 10 out of over 42. And the odds ratio, which is probably not going to be all that much different, is equal to 0.70 divided by 0.23, and it's 2.95. Okay, a little bit different. Okay, now we'd expect that we're kind of encouraged now that paper might be a little bit riskier than using those hot air machines. By the way, I'm not even really sure that's true, because can you imagine you put your hands under there, blows stuff all over the place, and who knows who touched them? I'm not convinced they're any more sanitary than paper is. But at any rate, this is a pseudo study. It's not a real study. So now we would have expected that to be a 1 if there's no difference, or close to 1. We'd expect the odds ratio to be a 1 if there's no difference. Okay, so now we're going to take a closer look at that to decide whether or not that's different enough from 1 for us to reject the idea that there's no difference in risk between using paper and hot air. But before we do that, I'm going to create another table, another 2x2 table, which is going to give me, based on what we see up here, my expected values. Well, the way I'm going to do that is I'm going to look at everybody together, not just the people that use paper, but everybody in one group. So out of 98 people, 29 of them got ill, and 69 of them didn't get ill, right? So what's the rate at which, what's the prevalence of illness in this group, right? It's 29 out of 98. Okay, good. So now we know that 46 people, I'm going to replace that with 46. We know that 46 people used paper. We know that 52 people used hot air. Okay, so out of those 40, if everything's equal, the rate of illness is the same for paper and hot air. Out of those 46, how many would we expect to get sick? We'd expect 46 times 0.295, right? We'd expect 13.61 people to get sick. Notice when I do the expected values, I'm not going to always get a even number. Okay, how about the people that used hot air? How many of them would I expect to get sick? I would expect 52 times, what percentage of the 52? Again, 29.59%. Okay, 15 to get sick. And the difference, the number of people that didn't get sick, is going to be equal to 46 minus the number of people that got sick, Got to add up to 46, and this has to add up to 52. So what I filled in here is I filled in my expected values based on what I observed in my study. So now my expected values are different than my observed values. The bigger the differences are between this 19 and 13, what's in each corresponding box, the bigger the difference is, the less likely that that's due to chance. Makes sense, right? If the differences between this box and this box is very small, probably that's due to chance. Just the fact that you're not always going to get the same numbers every time you do this. If the differences between this box and this box are large, then we would expect that that is less likely to be due to chance, right? So what I'm going to do now is I'm going to take the difference between each one of these boxes. Okay, I'm going to take this box, I'm going to take my observed value minus my expected value and put it down here. And over here I'm going to put my observed value minus my expected value for this box, put it down there. Then I'm going to put over here, I'm going to put my observed value minus my expected value, put it in that box, and my observed value minus my expected value, and put it in this box. Okay, now if I add all these together, what am I going to get? I'm going to get 0, right? So it's not going to help me very much, is it? Now, one of the things that we do to avoid that previously, to make sure everything had the same sign, is we squared these things. So I'm going to take each one of these things and I'm going to square it. Okay, I'm going to say that this one I'm going to say that this cell represents this times itself, and this cell represents this difference times itself, so that's going to be a positive number. And I'm going to say that this cell is equal to this number times itself, and this cell is going to be equal to this number times itself. Okay, so I've squared all of them. Now I'm going to take those and I'm going to add them all together. All of those differences. And I have a number, right? But that number is kind of, remember when we had this problem with some of the squares, that number is kind of exaggerated because we squared it. So now I'm going to take that number and I'm going to divide it by, instead, I can't use it quite that way. I'm not happy with that. So instead of doing that, I'm going to take each one of these differences between the observed values and the expected values, and I'm going to divide them by one of those numbers. I'm going to use the expected values. So I'm going to do this. I'm going to click in here, put in 29 divided by the expected value for that number. And down here, I'm going to put, let's see, this number divided by the expected value for that number. And I'm going to put in here, I'm going to put 29 divided by the expected value for that number, which was 32. And I'm going to put in 29 divided by the expected value for this number. And then I'm going to take these and add them all together. These are all the kind of adjusted differences, so that now they're all positive values. And I get a number 5.7. Take a look at this formula that I have right here. This is a number for chi-square. That big X, that big scripty X is a chi, a Greek letter chi capitalized. Okay, what does it say? Sum of the observed minus the expected values squared divided by the expected values. Okay, that is the value that I'm calling chi-square. Now, if the differences between the expected values and the observed values are small, what would you expect chi-square to be? You'd expect it to be a small number. If the observed values between the differences between the observed values and the expected values are big, you would expect chi-square to be a big number. So this value now is chi-square. I'm just going to write it in there kind of like that. That number represents our chi-square value, and it's basically all we've just done is used Excel to solve this formula for chi-square. Okay, pretty simple calculation. Not exotic, not complicated. That's chi-square. Now, the thing is now we have to decide whether or not that this number is big enough for us to say that the difference between the expected value and observed value are significant enough for us to say that there's less than a 5% chance of being wrong if we reject our null hypothesis. What's our null hypothesis? That there's no difference between the observed values and the expected values. Okay, so now just like many other statistics that we now have to compare to a critical value, what do we need to know in order to look up the critical value? Right? Well, with everything else, we needed to know what degrees of freedom. In chi-square, the degrees of freedom are going to be equal to the number of rows minus 1 divided by the number of columns times the number of columns minus 1. 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is 1. This is 1 degree of freedom. So I'm going to look up a chi-square table. Okay, and I should be able to find it here pretty quickly, I hope. Chi-square. Come on up. And if I can't find it, I can find it online pretty quickly, I'm sure. Here we go. Let's see if we, okay, here's our chi-square table. Degrees of freedom, and for a probability of a larger value chi-square, in other words, probability of a type 1 error, 0.05, our chi-square value that we need to exceed, our critical chi-square value is 3.84. Your table in your book is probably not going to have this many columns. Probably going to be more like something like this. Let's see if I can see this. Oops. Okay, area to the right of the critical value or bigger than the critical value, 3.84 for 1 degree of freedom. That's our critical value. Did we exceed our critical value? Is 5.7 bigger than 3.84? Yeah, so we did exceed it, right? Everybody agree? Okay, I didn't hear from that end of the room that we agree, right? We exceeded the critical value. Okay, so what do? We can reject our null hypothesis and accept our alternative hypothesis. There's a little bit of, one of the rules that we heard is that you need, each one of these boxes has to be greater than 5. Anybody remember whether it's the expected values or the observed values have to be greater than 5? Anybody remember? It's the expected values, right? The expected values can't be less than 5 in any one of these boxes. It affects the accuracy of the test. That doesn't mean absolutely you can't do it, but that's one of our expectations is that we don't want too small a sample in one of these boxes. The other thing about this is that you notice that the expected values, we actually have a fractional number like 13.6 and 15.4, right? We can't have that when we're counting individuals, right? There's a problem here. This is a continuous number, and this is an integer. So many times, if it's for the most part, you may be able to ignore this. But if it's a close calculation, if it's close, you may want to apply something called a continuity correction. And what that is that when you take your observed minus your expected values, take the positive value of it, and you subtract 1/2 from the difference before you square it. Okay? Then you square it and divide by e. That makes that number up here a little bit smaller. That makes it harder for you to reject the null hypothesis, right? So using the continuity correction makes it harder to reject the null hypothesis. It's a more conservative approach. If you have a really big sample and you really get a big chi-square value, probably it wouldn't have any effect on what you're going to do anyway. And most of the time you may be using SPSS or some other software to do the calculation anyway, so it's not a big deal to do the continuity correction. In fact, probably the software will do it 9 different ways that not even interested in doing it, in addition to with and without the continuity correction. So I didn't use the continuity correction here, but don't hang me. It should be okay. This pretty big chi-square we got here, right? Well, what am I going to do now? I'm going to do the same problem using SPSS. And that other file that I just uploaded is an SPSS version of this whole thing. Okay, paper versus air.sav. Let me see if the guys online are having any issues there. Okay, I can't, because we have that session going on upstairs, I really can't go over it again, unfortunately, the expected values, but you'll be able to go back on the recording and replay it. Okay, and it's a short session, so I'll be able to get it up real quick. I won't have to divide it up into 2 sections. Okay, so I'm waiting for Excel to open that up, and hopefully get rid of this, and here it comes. Okay, and this is the same data set that we were using just now. Okay, now I'm going to go into Analyze, and you'll notice that this actually lists all 98 individuals in this study. This person uses paper and became ill. This person over here uses paper, didn't become ill, and so on and so forth. Right, so they're all listed here. Okay, I'm going to say Analyze. There is actually a way to use SPSS to just put in the 2x2 table, but in this case we actually have the individual data, which is kind of the way you would probably collect it. So I'm going to go to Analyze. I'm going to go to Descriptive Statistics. This is not a mean that we're doing, right? Okay, this is not parametric statistics or kind of statistics that we're going to find means and compare means. I'm going to go Descriptive Statistics. I'm going to go down to crosstabs. You may remember we may have used this to lay out tables when we were doing our diagnostic tests, which are 2x2 tables. Crosstabs, and I'm going to go into crosstabs, and I'm going to put the exposure into the rows. In other words, what is the exposure? Are they exposed to lead, not exposed to lead? Are they taking a drug or taking a placebo? In this case, did they use paper or did they use air? The type of hand dryer they use. And the outcome I'm going to put into the columns. They got ill, or they became ill, or they didn't become ill. I'm going to click that in there. Now I'm going to go up to cells. And right now, the only thing SPSS is going to do for me is it's going to calculate the observed values. Okay, it's not going to do anything else for me. I'm going to click OK because I'm going to do this in a few steps so you can see the process. Okay, so here we go. And SPSS calculated these the cases, 98 cases. And look at this. Paper, 19, hot air, 10 out of 46, and so on. It created the table that we started from, right? That's all it did so far. Now, I'm going to go back up here to Analyze, Descriptive Statistics, go back in the crosstabs. I'm going to go with the cells again, except this time I'm going to ask it to give me the expected values. Okay, I'm going to click Continue again. Click OK. Okay, this time you'll notice that, oh, look, it filled in the counts for the observed values. It calls them counts, the observed values, and it gave me the expected counts as well. 19, 13.6. These numbers should look familiar to you, right? The same thing we just calculated in Excel. 10, 15.4, 42, 36.6, 27, 32.4, and so on. Okay, so now next thing I'm going to do, I'm going to go to Analyze, Descriptive Statistics, crosstabs, and I'm going to say, let's go into cells. I'm going to ask it to calculate the percentages by rows. Okay, what am I going to get now? I'm going to get my risks. Right? I'll do that again. Cells, I'm going to say calculate percentages by rows. Well, it'll be once you see it, you'll see what it's doing. Okay, and what did I get? Oh, well, look at this. Percentages by rows. 41%, right, of the people that used paper got sick. 19% of the people that used hot air got sick. And you guys remember how we calculated relative risk? 41 over 19, it came out to be 2 point something, which is what this is going to come out to be as well. See, it's doing the same thing we're doing, not doing anything exotic. These calculations are that straightforward. Okay, I'm trying to take a little bit of the mystery out of this. So I'm going to go back up here. I'm going to go Analyze Descriptive Statistics, and this time I'm going to go into crosstabs, and I'm going to go into statistics this time. I'm going to ask SPSS to calculate chi-square and to calculate risk. And I'm going to click Continue. And then I'm going to click OK. Well, now it's going to give me the same table I had before, except this time it's going to calculate my my risk estimates, odds ratio, and risk estimates. It says odds ratio directly. It says odds ratio for type, hand dryer, paper versus hot. And what was our odds ratio before? It was 2.9, same number we got. What was our relative risk? Now, for relative risk, it kind of disguises it a little bit. It calls it for cohort developed respiratory illness, okay? And that is 2.148. This number that winds up in the second row is always going to be your relative risk. The first number is obvious because they call it odds ratio. 2.956 is your odds ratio, and 2.148 is your relative risk. Well, now I want to decide whether that's a big enough number. It's different enough from the number 1 for me to say that that odds ratio has that if I were going to say my null hypothesis is that the odds ratio is equal to 1, for me to reject the idea that it's equal to 1. Well, let's see. What did it calculate for me? Based on kind of doing this binomial distribution. Remember, there's you got ill, you're ill or not ill, and these are all binomials. You're ill or you're not ill, or you use paper, you don't use paper, and so on. It calculates a confidence interval for me. So the confidence interval for the true odds ratio is 1.195 to 7.31. What's not between those two numbers? 1. So I'm 95% sure that the odds ratio is not 1. So I can reject my null hypothesis. How about for relative risk? I'm 95% sure, because 1.11 to 4. That the relative risk is not 1 again. But if my odds ratio, if my confidence interval includes within its range 1, I can't be more than 95% certain that it isn't 1. Get it? Okay, that's kind of one way for us to do this. The other way for us to do this is to calculate a chi-square. The kind we calculated, the simple version, is called Pearson's chi-square. Anybody remember what it was? 5.7. Same thing that they got, 1 degree of freedom. What's the probability of getting that large a chi-square value with 1 degree of freedom if there's no difference between using paper and using air? What's the probability of having a type 1 error if we reject the null hypothesis? The probability is 0.17. That's less than our acceptable level of error, which is usually about 0.05. So since this significance is less than 0.05, we can reject the null hypothesis, just like we were talking about before. Because when we did it with Excel, we couldn't actually calculate this easily. We were forced to use the actual value for chi-square, the critical value for chi-square. And if I did it with the continuity correction, I get a smaller chi-square value, but it's still significant. It's still 0.03. So it works both ways. Okay?
Is chi-square just one-sided?
Isn't that's interesting? Exactly right. It's one-sided. However, it always tells you that it's two-sided over there. Technically, it could be two-sided in a sense, but really it's kind of a one-sided calc. You're only looking at one end ever. Okay, but yeah, ignore that. That's just like SPSS has a tendency to word the output for statisticians, and it makes it a little confusing. It uses a technical reason for calling it two-sided there, but really effectively the way that everybody uses it, it's a one-sided thing, only bigger. Goodbye. You guys got to go upstairs now. Okay, we have a guest. We don't want to keep him waiting. We're at 201, room 201. Okay, get moving. Okay, and you guys that are online, please switch over to the Adobe Connect site, and we'll be getting started upstairs.